Welcome to this episode of the Verilog Bench. Today we're going to be looking at the AMBA Core Specification from the RTL and verification perspective. This is the RTL and verification cut for IHI0011A. The center of gravity is AHB because that is where most of the implementation complexity lies, but we will keep ASB and APB visible so the hierarchy remains coherent. The goal is to leave you with an implementable mental model of the buses, responses, and block responsibilities. The first implementation guardrail is timing style. AHB timing is defined from rising edge to rising edge. ASB timing is defined from falling edge to falling edge. APB transfers always require 2 bus cycles in this revision. That difference matters immediately when you design bridges, assertions, and waveform checks. Chapter 2 is not optional for implementers. The prefixes already tell you a lot about how the buses are partitioned. AHB collects control, data, and arbitration signals under H prefix names. ASB separates some roles with A, B, and D prefixes, while APB stays deliberately small. The core AHB mental model is a one-cycle address phase followed by a data phase that can stretch with H ready. Address and control move first, and the next address can overlap the current data phase. When H ready goes low, the current data phase stretches and the next address must stay stable until completion. That means every monitor and subordinate implementation must separate address legality from data completion timing. AHB requests are defined by more than an address. HTrans identifies the transfer category. HSize and HBurst define width and beat pattern, and HProc carries access attributes. These controls are part of the address phase contract and must remain consistent with the later response and completion behavior. Completion logic is where many AHB bugs live. A weighted non-OK response uses H-ready low on the first cycle and HRESP across the full 2-cycle response. HRESP distinguishes OK, error, retry, and split. Retry and split are not just error flavors. They drive manager state changes and often rearbitration. Your verification model has to capture that behavior explicitly. The original document uses master and slave terminology. In this video, I will use manager and subordinate. One reason AHB scales well as a reusable interface is that block ownership is explicit. Managers initiate traffic. Subordinates return data and status. The arbiter selects ownership. The decoder selects the destination. When bugs appear, knowing which block owns which rule makes debug and sign off much faster. Width and Endianness are easy to handwave and costly to get wrong. The document is explicit that active byte lanes depend on transfer size and system Endianness, and that all modules on the bus must agree on that Endianness. This is a design rule, a bridge rule, and a verification rule all at once. ASB is not just an older spelling of AHB. The buses share architectural goals, but the timing style, decoder role, and transfer handling differ enough that you should not recycle AHB assumptions blindly. In particular, decode cycles and the decoder state machine matter far more in ASB reasoning. On the peripheral side, the main implementation block is the APB bridge. It latches address and control and setup, generates the select and enable sequencing, and moves data between the system bus and the peripheral edge. The timing view here shows one write transfer followed by one read transfer, so you can see address hold, write data hold, and read data return in the enable phase. If your project uses both AHB and ASB bridge paths, both deserve explicit test coverage instead of assuming one path proves the other. Chapter 6 is best read as verification infrastructure. It tells you that modular test and diagnostic access were considered part of the AMBA architecture from the start. That does not make it the main protocol chapter, but it does make it relevant when you build a complete verification plan around the buses. The RTL takeaway is to separate responsibilities cleanly. Give AHB the depth it needs. Keep ASB distinct rather than treating it as a near clone, and treat the APB bridge as a critical integration block. Most late surprises come from response handling with adaptation and assumptions that leaked from one bus style into another. If this RTL deep dive was useful, like and subscribe to be notified of future videos. The next cut keeps the same Rev 2.0 architecture, but shifts to what software and bring-up engineers actually need to understand. To close, here is a glossary for the core bus family acronyms. AMBA stands for Advanced Microcontroller Bus Architecture. AHB is Advanced High Performance Bus. ASB is Advanced System Bus. And APB is Advanced Peripheral Bus. RTL means Register Transfer Level. DMA means Direct Memory Access. TIC means Test Interface Controller. SoC means System on Chip, the integrated platform where these buses and verification rules come together.